So I'm Dr. Dominik Kubicki. I work in the School of Chemistry at the University of Birmingham in the United Kingdom. I joined the school very recently. I'm an assistant professor. So my research focuses on new solar cell materials. There is a big challenge currently that society is facing, which is the energy crisis. We are trying to develop new types of solar cells, and solid-state NMR plays a critical role in understanding how these materials behave, the structure, how they degrade. So this is what our research is currently focused on. So the unique thing about solid-state NMR is that we can look at specific types of nuclei within the structure. We can look at them quantitatively, and we can understand the local structure. So solid-state NMR is a local structural characterization technique, which is very different from many other techniques like X-ray diffraction or neutron diffraction that we use in the field. When we make new solar cells, the halide perovskite type solar cells, we add dopants, very dilute species, for example, one on the order of 1 mole%. And seeing these very dilute species with diffraction techniques is essentially impossible. So being able to focus our attention on a specific element with NMR has been key to addressing these challenges. So halide perovskites have emerged about 15 years ago as a new class of solar cell materials. And we've been very excited about this class of solids because just within 10 years, their efficiencies went from over 3% to over 25%. So they are now comparable to silicon solar cells. But there are still challenges. For example, they are not as stable as silicon. They degrade relatively easily. So solid-state NMR has been really useful to trying to understand the atomic level mechanisms, the processes that lead to degradation of halide perovskite solar cells when we expose them to, say, ambient air or light, and then trying to use this knowledge to design better solar cells. So what we do in my lab, we make materials, which are good solar cell materials, they absorb light, and then we try to degrade them to understand what is the underlying chemistry that leads to the degradation of the properties. We are facing an energy crisis today. We are trying to diversify the energy sources. We are trying to move away from coal and try to use more of renewable energy sources. And solar cell energy is one of the most viable alternatives because there's over 1,000 times more energy, solar energy hitting the surface of the Earth than we actually need, than we use at every given moment. And also you have to remember that there's currently people in the world living without access to electricity. So using solar cells to give them access to electricity is one of the best ways to go forward. So the halide perovskites we use, they are very complex mixtures of chemical elements. They have at least 5 or 6 different components, various additives, dopants. It's a very complex chemical mixture. And analyzing this is an extremely challenging task. Using optical spectroscopies or X-ray diffraction doesn't give us the answers we are looking for. So solid-state NMR, by virtue of allowing us to focus our attention on a specific isotope and understand it quantitatively, has been really a game changer for understanding what is happening to each of these components in a functioning solar cell. One of the biggest challenges is stability. If you think about silicon solar cells, the silicon technology, we have to guarantee that they will work for at least 25 years. With halide perovskite solar cells, we are currently at the 1-year mark, but it's still fantastic that just within 5 years, we were able to bring the stability from days or weeks to over a year. So I think the next big challenge is how do we go from 1 year to 10 years to make the step change. Finding new materials, finding new ways of stabilizing them. One of the ways we stabilize halide perovskites is by using additives, trying to identify new additives, understanding what they do to the material that makes it more stable. Currently, we use a lot of trial and error approaches, and being able to understand the atomic level microstructure and how it relates to the properties has been key to developing new materials in a more rational way. One of the big research questions is what happens to these materials when we expose them to ambient air, humidity, ambient light. This is the conditions that degrade these materials. And one of the ways we've been trying to go about it is to develop in situ NMR strategies, whereby we put a functioning solar cell device into a rotor and try to understand how its structure changes in real time with NMR. So this is something we currently work on. There are also other achievements that have already been published that are out there. For example, in collaboration with Ted Sargent from the Northwestern University, we've been developing new tandem solar cells. A tandem solar cell is a very exciting device in which we stack different solar cell absorbers on top of each other to harvest the solar cell spectrum more efficiently. So they've developed new type of compositions, and solid-state NMR has been critical to try to understand why these compositions work so well.